hold on, let's see. It's still recording. I think it's working. All right. But this is stuck. Now? Okay. So we talked about deviation from Beer's law a little bit last time. So in order for Beer's law to be applied, we are limited to concentration. So if we have really high concentration, then molecules are going to be in close proximity with each other. And if they are in close proximity with each other, their electrons might start to be shared, and there will be interactions. That is going to impact the absorptivity of this molecule at a particular wavelength. So that's why oftentimes you dilute your sample so that you get into a working range that you know you have linear relationship and you know you can use Beer's law. Another aspect that might deviate from Beer's law is if you have molecules that can dissociate. So that will have functional groups that can dissociate, or they can ionize. For example, losing a proton, gaining a proton, losing an electron. So if they are highly dissociable species, and if they can ionize in a certain unbuffered system, then again, the ions won't absorb light at the same wavelength as the original atom or molecule. So working in a buffered system when we have ionizable species is recommended. Polychromatic light, that means your light that is reaching your sample has not been filtered into a monochromatic light. That means you have multiple wavelengths. So your absorptivity is not unique. In Beer's law, you have the A for absorptivity, B for path length, and C for concentration. So when you have multiple wavelengths hitting the sample, you have multiple absorptivity. So what absorptivity will you use in your equation? So that is not known. So we cannot, that's why it's very important for Beer's law to have one wavelength or wavelengths that are very close to each other with similar absorptivity, for where the analyte has similar absorptivity, I would say. Okay. So procedural consideration, that means when has to do with sample preparation. So when you're preparing your sample, since you're working with absorption of light and fluorescence of light, you want to make sure your sample is homogeneous, that's important, and clear. If your sample is cloudy, we talked about it last time, it means that there are a lot of particles are going to scatter light. And if a lot of particles are going to scatter light, you're going to get false high absorption. So oftentimes we have a centrifugation step that is associated with sample prep if our sample matrix have a lot of particulates in it. Reference cell and appropriate control, that's basically having a blank, which you will do in the total carbohydrate lab, where you're going to have a blank that contains all of the reagents except for your actual sample. And we talked about that last time. We want to correct for any light diffraction or scattering that comes from reagents, not your analytes. And then chemical modification, like I said, in your blank, you need to make sure you have the same reagents as your sample. And then you correct by that. We call it zeroing, blanking or zeroing. Okay, sample holding is important. Look at these two sample holding cuvettes. So one has this interior smaller diameter. If you're limited with sample amount, let's say you don't have a lot of sample, so, and if you put it in a cuvette with wider opening, you might not get enough sample in there where the light of path or path of light doesn't go through your sample. So the light goes above where you don't have liquid. So you want to make sure to use appropriate cuvettes based on the sample size you have. The other important factor is the type of the holding cell. So quartz and fused silica are usually used with UV detection, whereas glass and plastic, they absorb UV light. So you don't want to use them when you are measuring absorption under UV light. So you can use glass and plastic for visible light. So selection of appropriate wavelength. If you remember when we did the HPLC lab, we selected something we call lambda max, which is the wavelength at which you get highest absorption. That's we are maximizing sensitivity. So if we're measuring at 272, we got the highest response. If we measure at 250, we'll get a response, but it will be very, very small. So if we have reduced concentration, we won't be able to detect it. So we want to maximize sensitivity by selecting the wavelength at which we have the maximum absorption. Now, and the other thing is, sometimes to enhance sensitivity, you know, we have these filters. So your chromator or monochromator, you will have the grading system, and then you will have the light that comes off at different wavelengths. And then you have an opening that allows a narrow range of wavelengths to go through and get to your sample. Sometimes you can make it a little wider. You can make it a little wider so you can have higher intensity of the beam, especially if you have wavelengths where you get maximum absorption at 270, 272, 274, 269, you still have the same maximum absorption, so you can widen the slit to have more intensity of light entering and reaching your sample. You can enhance sensitivity and lower your threshold by doing so. And oftentimes, you need to calibrate your instrument to reduce the noise. And by doing that, by calibrating the instrument, is you would block the light source and then calibrate it to have zero transmittance, no light is passing through. And then you also have 100% transmittance when you either put a blank in there and you zero and say, okay, as it goes through the blank sample, this is our 100% transmittance. Or if we don't want to use a blank, you can just leave the cell empty. But usually it is done with a blank. Okay, so again, it has to be linear to obey Beer's law. So we choose concentrations that give us linear relationship with the absorption. So if we have a linear relationship, we're good to go. And that's why it's very important when we dilute our samples to fit within the linear range. If we dilute our sample and not enough and we get absorption here, I mean, it's out our concentration at 12, for example, molar, or whatever that absorption is, millimolar. That means it's outside of the curve. We don't know if this curve is going to plateau afterwards. So we cannot make measurements in this region. We have to dilute more to fit that linear range. So this is linear, this is nonlinear, and every analyte have a different linear range. So some analytes are linear between 2.5 and 10, others are linear between 0.5 and 3, for example. So it depends on the analyte. It's very specific to the analyte. Those of you that did the AA, calcium and iron had different concentrations for their linearity and absorption. Okay, so this is a complex thing that I'll try to explain very slowly and carefully. So we said we use a blank, right, to correct for differences due to reagents. But sometimes your sample itself is very complex. You have multiple interfering components in there that might result in different untrue absorption or overestimated absorption or even underestimated absorption. So in this case, we follow what we call standard addition. Standard addition method, which is a complex calculation a little bit, but it is not that hard to do. And so in this case, what you do with standard addition is, I'm going to illustrate by drawing whatever is written there. So let's say we're going to produce a standard curve with 5 different concentrations. So what I would do is I get, see, I'm very good at drawing, volumetric flasks of the same size and shape. Okay, so that's 5. Again, of the same size and shape. And then you add to each one of them volume of unknown sample. The same volume of the unknown sample. Okay, the same. And then, so you would have exactly, like if you're going to put, depending on your dilution, let's say 10 ml, and you are diluting to 100 ml. Okay, so you put 10 ml of your sample in all of them. And then you add your standards, but in each one you will have a different volume of a standard. So, and then you add a different volume. By adding a different volume, then you are creating a calibration curve. You're creating a solution or a standard solution that is of a different concentration in each one of them. Okay, so that's your standard curve is being built with your sample in it. And then you bring all of them to the mark. All of them have the total volume, which is 100 ml. You measure absorption, and then you plot absorption over volume of your standard. And then that would be your equation of the line that has a constant. And then everything in here is the volume of the standard, the concentration of the standard, which are known, and then the volume of the unknown, which you know, and then the concentration of the unknown, and then the total volume. So you know everything except for the concentration, and you solve for that. Okay, you do that standard addition for samples that are complex in their matrix. Okay, instrumental error. Indiscriminate error. Indiscriminate error, we often call that noise, instrument noise. So logically, which one of these would be correct? Just wild guess. Huh? I can't hear you, Keaton. A is correct, but it's not the only correct answer. So all of the above, I was going to say. Okay, so it has to be relatively small noise. So your absorption, that deviation from the correct absorption should not exceed 5% of the actual absorption. So 1.5 to 5% of the actual absorption value is what we call acceptable noise. We can test that by doing a repeated measure of the same sample, so that is correct. And we can reduce it if we use intermediate concentration. So there is kind of a rule of thumb. We say if your absorption is between 0.2 to 0.8 absorption units is acceptable. If your absorption is 2.5, this is way too high of an absorption. You better dilute your sample. Okay? Now there are cases where you can go up to 1.5 in absorption, depending on the method and the noise associated with the instrument that you're using. But oftentimes, absorption between 0.2 and 0.8 is your target. Anything below that, if you get an absorption of 0.05, this is really close to your noise, the instrument noise. You cannot really trust absorptions that low. So you might want to concentrate your sample to get higher absorption. All right, let's talk about instrument setup in spectroscopy. So very simple. You start with a light source. So in general absorption spectrophotometers, you would either have a tungsten lamp for visible light or a deuterium lamp for UV light. And then your light that is composed of multiple wavelengths is going to go through your monochromator. And in there, your light is going to be diffracted using a grading system. So that's the light going in, a mirror, and that's your grading system. Sometimes there is a prism. We'll do the same thing. And then it will diffract the light, and then another mirror will reflect the light, and then there is an opening which allows a very specific narrow range of wavelengths to go through. Okay, so, and this slit you can select oftentimes, many times, unless it's a fixed UV wavelength detector. You can select where that slit goes to allow different wavelengths to pass through. And remember last time, sometime we said that we have mirrors. You want to make sure everything fit in a small box and the light goes in and goes out the different direction. So mirrors usually are used to reflect the light. And then a monochromatic light will pass through your sample, and then transmitted light will get to your detector, and then the detector will, sometimes you have an amplifier, and then mathematical calculations occur to convert transmittance to absorption. So the detector oftentimes is a phototube detector, and here's what it is. So your light will hit the light that comes out, or the transmitted beam that comes out of your sample will hit a cathode, and then an electron jumps off the cathode and is acquired by the anode, and you get an electrical signal, and that's what the readout is. So, but many times you have an amplified system where you have a photomultiplier, and that's the same detector you had in your AA instrument if you ran the AA lab. In an amplifier, it intensifies the signal, enhances the sensitivity, and reduces the threshold. So what happens in this case, your light hits the cathode, it emits an electron, it hits a dynode which multiplies the number of electrons that comes off of it. Another dynode, more electrons, you have a more powerful signal. Process of amplification. Okay, I'm putting some of you to sleep. I know this is not a very exciting topic, but let's try to stay awake to understand what's going on. Okay. All right, so a photodiode, we talked about that for HPLC. What it does, it generates a spectra. So in this case, the diffraction of light doesn't occur. All the light gets projected to your sample, and then from there, after it gets, the transmitted light gets diffracted. And then you have multiple wavelengths now that they hit the detector, and you get simultaneous absorption at different wavelengths, at a broad range of wavelengths. So per 0.1 second, you would get absorption over a wide range of spectra, and this is what we call, this is your fingerprint that we talked about in the HPLC lab, where you get not only absorption at one selected wavelength, you get absorption at all the range of wavelength that you've selected, from 200 to 50 to 600 or whatever. So types of instrument, you can have a single beam or a double beam. In a single beam instrument, you don't have two cells, you only have one cell. You would first put a blank and zero with the blank, take the blank out, and put back your sample. So in this case, though, there's an advantage that you don't split the intensity of the light. You would have high intensity of the light. But a disadvantage is you will have instrument noise from when you zeroed to when you read your last sample. So you will have an incremental change in your absorption over time, especially if you're running 50 samples, let's say, and you zeroed at the beginning, then you start seeing noise accumulate. The double beam, you actually have two cells. Light gets split. One goes to your sample cell, one goes to your reference cell, or the blank. And then both reach the detector, and you get absorption of the reference and absorption for the sample, and you get a reading that is actually subtracting the reference from the sample, or vice versa, depending if your blank has the higher absorption or the sample has the higher absorption. So you get the difference, and that would be your sample absorption. So you would have a correction throughout the analysis, and you don't need, and there won't be instrument noise that builds up. But the disadvantage is you reduce the radiant power because the light is split. This is a table correction from your slides. It's not chapter 24, chapter 7. So this is just giving you an idea of how different functional groups absorb maximum at different wavelengths, and then they have different absorptivity. And like I said, if you have the absorptivity for that molecule, even if you don't have a standard curve, you can actually measure concentration by having the absorption, and you will have the path length, and then you will have the absorptivity if you know what you're looking for, and then you can solve for concentration. So in fluorescence spectroscopy, it's a little bit different because we are measuring the emitted light rather than the transmitted light. So in fluorescence, of course, absorption needs to occur first, so there is what we call an excitation wavelength. And then we have the emission wavelength at which we are detecting the fluorescence or the emission of light. So in this case, you have the radiant source or radiation source. So you have the wavelength isolator, in other words, monochromator. And then you get your incident beam that is one or a narrow range of wavelength that hits the sample. And then there is the transmitted light, which we don't care about. The the emitted light, or the fluorescence, now gets directed at a 90 degrees angle by mirrors. And then you get another monochromator here, wavelength isolator or monochromator. You're selecting the emission wavelength because you want to measure emission at a particular singular wavelength. And then you get into your detector, you measure, convert to electrical signal, and you have a readout. So that is the difference in fluorescence instrument, is that you would have this angle where you don't measure transmittance, you measure fluorescence. That's it. You know what you guys doing for the lab. So finally, I'm going to start AA. Stretch. Wake up. Okay, new subject. Well, not very new, but related, applicable. Most of you already started the AA, so you know what I'm going to talk about. You might as well come lecture. Who wants to volunteer? What? Okay. I can, if you come give the atomic absorption lecture, I can give you 25 over 25 on one of your lowest grade quiz. No. So any volunteers? I didn't think so. Okay. So I'll be the one boring, talking, and putting you to sleep. But okay, an atomic absorption or atomic spectroscopy, you either measure absorption or emission. So you can do either. So you can have either atomic absorption spectroscopy or atomic emission spectroscopy. In atomic absorption spectroscopy, you can have a flame atomic absorption like you did in the lab, or most of you did. Or you have the electrothermal, which we do have in our instrument, but we didn't do. And there are some differences between the two, and we'll talk about that as well. In emission, you can do flame emission, or you can do what we call inductively coupled plasma atomic emission spectroscopy. It's a mouthful, but it is written in one of your slides, and we'll talk about that. So the use of atomic absorption is really narrowed down to determining your mineral nutrients, including those that are toxic. So minerals that are considered essential for us, in addition to those that could pose a health concern. So here's your wonderful table that you all like. But what the purpose of this here is the AA cannot measure every element. Okay? So it mostly measures those that can be in metallic form. So the pink, everything highlighted in pink can be measured by atomic absorption. So among them are our essential nutrients that the body needs. Among them are toxic, like the lead, mercury, cadmium, nickel. And then the USDA nutrient base has a lot of these important elements, data for different foods. So we'll find a lot of different foods with the data, but the database is not complete for all the foods and all the minerals. So in atomic absorption, do we have vibrational energy? No, we don't have vibrational energy. Why? I said that at the beginning of the lecture. Let's see who remembers. Okay, Sarah? The diagram, but okay. Yes, but?
Since they're in atomic form, there's no bonds between the atoms from which the vibrational energy.
Yes, so this electronic energy does occur in molecules. So molecules and atoms within a molecule can attain electrical energy change, electronic energy change, and can attain vibrational energy change. But atoms can only attain electronic energy change. And the absorption has to be measured for the atoms in the neutral state, not the ionized state, and in the gaseous state. So those of you that did the AA, you saw that you had to aspirate your solution, evaporate the solvent, and also break down the bonds to release the atoms in the gaseous state and stay in the flame, where they get excited in the flame. And the radiation is often, or is always, I would say, in the UV visible range. So no other range for measuring absorption or emission for these atoms. So every atom has a unique spectrum like any molecule. So there is a unique wavelength at which absorption occurs for every element, as well as fluorescence for every element. So every element that we measure can absorb and then fluoresce light, and fluorescence happens at longer wavelength. So this would be the absorption. The wavelength would be wider for fluorescence. And then the absorption of energy should fit within the allowable energy spacing for electronic. So we don't have vibration and we don't have rotation. So the vibration and rotation do not exist for atoms. We only see changes within their allowable electronic energy shifts. That means we don't have vibration or rotation. So there are certain steps for atomic absorption or atomic spectroscopy in general to occur. So you have your samples where your minerals are in compound or molecular forms, and they are in solvent. So there's your aspirator that aspirates the sample into fine mist, and now your mist is in the flame or plasma. Okay, what you did in the lab, or a couple of groups still to do in the lab on Wednesday, you will see a flame. Your mist is going directly into the flame. Then we have vaporization of your solvent and breaking of bonds to give you the singular atoms in the gaseous state. So it's very important that your atoms are in neutral atom form and no ionization occurs. Ionization could occur if you have really a flame that is very high in temperature. So if we have ionization, you end up with ions, not atoms, and they have a different absorption spectra. So often if you get ionization and you're measuring at the optimal wavelength for a particular metal or element, you will get an underestimation. So those of you, again, that did the lab already got introduced to the hollow cathode lamp, which is basically a hollow tube that is filled with a neutral or inert gas, argon or neon. And then you have the anode that is tungsten, and the cathode is made up of the metallic form of the element. So when the energy hits that metallic form or the cathode, it's going to emit radiation within the wavelength or within the spectral wavelength of your element. And because we have a cathode specific and made up of the metallic form of your element, we need to have a specific lamp for each element for the most part. Some lamps would have two cathodes in them and can be used to determine two minerals like the calcium and magnesium, for example. The electrodeless discharge lamp is basically, it's a hollow tube again. It has inert gas, similar to the hollow cathode lamp. And the discharge, however, is produced by radio frequency generator versus an electric current. That's the only difference. And it's used mostly for volatile elements. These used to be the older version of the atomic absorption. I don't have a picture of the new one. But that was the oldest, second oldest, and they both are gone right now. Right, Cindy? Or we have one in storage? Okay. The one that is not very ancient is in storage. The one we have in the lab now is most recent, and you can put multiple lamps at the same time rather than having to change the lamp each time. And also it has the graphite and the flame, so you can do both types of atomic absorption. Again, here's a general principle where you have your sample, your sample, the tubing where sucks the sample into the nebulizer. The nebulizer makes the liquid into a mist, converts it into a mist, and puts it into the flame. And in the flame, you break the bond. I see Riley's hand up.
I have a question about the hollow cathode. So that hits the sample before it enters the flame?
The cathode lamp?
Yeah. I guess I'm kind of confused where that comes into play.
Okay, I think I have an illustration. No? Did I illustrate it at all? No? Oh, it's right here. Okay, it's right here. Gosh. Okay, so what happens, Riley, look at this diagram. Okay, so your sample gets aspirated into the flame. So now you have the flame breaking the bonds. So your atoms are in the flame, gaseous form. There's the lamp source. Okay, so the light is going to go projected into the flame. So the atoms in the flame will get excited and will absorb light at particular wavelength. And then the transmitted light, there is a monochromator here. It doesn't show. You're going to diffract the light into singular wavelength, and only one wavelength that you're interested in for that particular atom is going to reach the photomultiplier tube detector. Okay? So your atoms are in the flame and the light is projected towards the flame. So the flame is atomizing and the lamp is exciting. That means giving the energy so that the atom goes from ground state to excited state. And then we apply Beer's law. We convert the transmission of light, taking the log, and then we relate that to absorptivity, the length, the path. In this case, your flame is your cuvette, and then you can get concentration. But usually we run standards, and then we measure absorption of the standards and construct a standard curve. So again, another illustration here where you get the monochromator that isolates the wavelength of interest and measure it, and you can see that the change in the spectrum of a specific element is due to absorption of light at that specific wavelength. And then your detector, oftentimes for AA, atomic absorption detector, is a photomultiplier tube detector. So the photomultiplier is, as we explained earlier, it just amplifies the signal to enhance sensitivity. So the graphite. So when you have a graphite, it's the same system except you have, instead of the flame, you have a surface area, where you call it the graphite tube, where the surface is heated. You have a platform that gets heated at really high temperatures. So really the benefit of having this graphite tubing is when you have really small amount of sample. So, you know, when you aspirate your sample, you have about 10 ml in a tube, so you have a luxury to aspirate sample into the flame, but sometimes your sample is like 1 ml. You don't have luxury to aspirate and take your time to measure in the flame. So you would have to put it on a surface, let it, the platform, the heated platform is going to vaporize solvent, vaporize the element in the atomic form, break down the bonds, of course, and then they will be at the upper level of that tube, and then the light is going to be directed to that area, surface area, above the platform, and that's where excitation occurs. So it is expensive to have this unit, and so the advantage is you have lower threshold and you have smaller sample size, so you can use it when you are limited to sample, but the disadvantage is you have lower sample throughput, so it's not as fast as you just put a sample, take it out, and put another sample. So it's really between every sample there is a time to make sure that you don't burn yourself when you're putting a sample on, and then just care. I never personally worked with it, but you obviously need to have it cool before you put a sample in. So that makes it more difficult to operate and sometimes lower precision and matrix interference. So, emission, flame emission. So again, here we're measuring the emitted light rather than the absorbed light. And in this case, when the electron goes back from excited state to ground state, you get dissipation of heat, and the remaining energy is emitted as photon with a lower energy and longer wavelength. Even, it's the same thing. You need atomization to occur. That means you need to break the bonds within a mineral molecule. And then you need excitation as well. But in this case, because it's called flame emission, you get to atomize and excite using the flame. There is no lamp involved. So only minerals or elements that are excited at low energy, sodium and potassium as an example, can be measured with flame emission. So those that get excited at lower energy. That means excited with the heat from the flame. So flame photometry specifically, you use low flame temperature, you have less interference, and you have a filter, not a monochromator. You have a filter to filter the wavelength of a particular absorption wavelength. I'll just introduce quickly ICP, and then we will pick up from here next time. An ICP, inductively coupled atomic emission spectroscopy. It is based on emission, not absorption, but in this case, you don't have a flame and you don't have a lamp. You have a plasma. So the plasma is basically argon gas that gets hit by radiation and gets ionized. So it gets ionized, so you would have electrons, negatively charged electrons, and you get argon gas, and you have less than 1% of non-ionized argon gas. So it heats up once the radiation hits it. It heats up pretty fast to really high temperature, resulting in vaporization and excitation at the same time. It gives you very effective atomization, but rarely any ionization. This is important. You don't get ionization with plasma just because the gas in there is full of ions. It has ions and electrons preventing ionization, further ionization of other atoms. And then the radio frequency is applied to the copper oil, and that's what gets the argon gas ionized. So with that, I'm going to leave you with that and continue next time. Come with a little bit more energy. Yeah, be excited like the atoms.